Hello everyone, warm greetings to each and everyone watching this video. My name is Manikanta from Weltech University, Chennai, studying second year MTech in Automobile Engineering in specialization with electric and hybrid vehicles in collaboration with ARAI Pune. Today I am going to present you a presentation regarding the final assessment test of powertrain management system, in which I will be discussing about the transmission system, mainly focusing on the automatic transmission. Let's go into the details.
As a part of transmission system, today I'm going to discuss about the automatic transmission. This is the outline of the presentation in which the title of the topic which I have selected is the transmission system, in which I have considered the automatic transmission, and I will be discussing about the need for the subsystem, why is it necessary, what are the emission norms, what is the pollution it is causing, how is the performance getting degraded uh, with respect to average fuel consumption, power delivered, ideal working of the system, and we'll also discuss about the mechanical subsystems and parts description and the design dimensions of the automatic transmission, and also we'll discuss about the electronics and instrumentation parts, which consisting of the elements or electronic subsystems, overall working and working algorithm of automatic transmission, and some vehicle details and manufacturers who are supplying the automatic transmissions, the OEMs list, and their um, place will be represented in this presentation. So getting into the details, this is the block diagram of a vehicle which is having a multiple subsystems. In this, as we can see, we the fuel storage system, fuel delivery system, air delivery system, combustion chamber, after treatment system, transmission system, wheel tire system, road tire interaction are there. Apart from this, at the bottom of this block diagram, we can also see the design constraints or limits, drivers demand, and emission norms. So what does these mean actually? So the total subsystem, what we are seeing at the top of the block diagram, are represented with respect to these three constraints. So the design constraints or limits comes under the whether the aerodynamic constraints or the size of the object, or according to the testing and certification of automobiles, each and every component of the automobile should be limited to a particular design and to be limited to a particular standards or dimensions. So those design constraints are to be kept in mind while manufacturing or fabricating an automobile. And driver's demand, whenever the name driver's demand comes into the mind, the only one thing which we come across is the clutch and declutch activation, and then the torque that is required to move on some grades and all. So these comes under the driver's demand, and means what the driver is demanding from the vehicle, means what are the aspects that the driver is um, experiencing, means whatever the things he want to get overcome. So those all comes under the driver's demand. And the last comes the emission norms. So what does this emission norms means? Emission standards are the legal requirements governing air pollutants released into the atmosphere. Emission standards set quantitative limits on the permissible amount of specific air pollutants that may be released from specific sources over specific time frames. So this is all about the three constraints which comes across the building of a vehicle. And now let's go into the different types of subsystems in a very short notes. And we'll be discussing more about the transmission system. Inside this transmission system, again, we'll be discussing, will be our main focus will be on the automatic transmission. So let's have a short notes of each and every subsystem. First comes the fuel storage system. So what does this mean? This is a very familiar name. What we know is a fuel tank. For every vehicle, we may or may not be aware of a fuel storage system, but everyone is aware of a fuel tank, which is called as a petrol tank or gas tank. That is a safe container for flammable fluids. Though any storage tank for fuel may be so called, the term is typically applied to the part of an engine subsystem in which the fuel is stored and propelled or released into an engine. And next comes the fuel delivery system. The fuel delivery system consists of all the components which supply the engine with fuel. This includes the tank itself, all the lines, one or more fuel filter, a fuel pump, and the fuel metering components. And next comes the air delivery system. The air distribution system is basically a mechanical system and consists of blower fans to remove air, ducts to carry air, and valves to control the airflow. Next, the combustion chamber. We are all very familiar with the word combustion chamber, which is the area within the cylinder where the fuel or air mix is ignited. As the piston compresses, the fuel or air mix and makes contact with the spark plug and mixes in the combusted and pushed out of the combustion chamber in the form of energy in case of SA engine. Next comes the transmission system. This is the part of the vehicle that connects to the back of the engine, offering power from the engine to the wheels. The transmission uses the power created in the engine to keep the wheels spinning and keep the engine within a certain revolutions per minute range. Next, the wheels or tire system. The wheel disc connects the rims with the hub and the rim holds the tire. And the road tire interaction, if we consider this as a magic formula, then it models the interaction between the tire tread and the road pavement. The longitudinal force arising from this interaction is given by the magic formula. After treatment system in engine is the major after treatment devices to cut down the emissions from the CI engines. Includes the use of diesel particulate filter, which is popularly known as the DPF, diesel oxidation catalyst known as a DOC, and lean NOx trap LNT, selective catalytic reduction SCR, or a combination of these. So either one of the above mentioned parameters or a combination can be used in the after treatment devices. Need for the transmission system. So why transmission system is necessary? This can be observed in the two figures shown over here. So vehicle needs a transmission system to transfer the power from the engine to the driver's shaft and differential to let the wheels turn. The transmission varies the torque, the speed, and the direction by changing the transmission ratios and enable the car to start with high torque. So if we consider these two parameters, two diagrams, actually the wheels where the wheels interact with the tires will be having the higher traction, means a lot of traction is required in order to overcome. So if we consider the case of the first figure, so in this figure all the gray line, whatever the gray line is present over here, this needs a lot of traction. And as we can see here, this is running in a gearless mode. So if we consider the figure 2, the gray line, whatever we have observed in the figure 1, has been almost reduced due to the utilization of first gear, second gear, third gear, and fourth gear. This means only the part where we are seeing the gray lines is having more traction, and the remaining part, the vehicle can move easily while uphilling. This is the important need for the transmission system. And the importance of transmission, actually, your car's transmission uses the power of your vehicle to move the engine at various speeds. There are two designs of transmission, which is automatic and manual. Automatic vehicles perform all the work for you, such as shifting from precise operating systems. This is the main importance of the transmission system. And then comes the emissions. What emissions does these causes? Of course, each and every transmission system, each and every vehicle causes some vehicles except the electric vehicles. So while we are considering these parts, emissions also comes into the picture. As with the consumption, a distinction can be made in the case of emissions between those caused directly by transmission and those which result from the engine, to which the ratio gives rise. The emissions from internal combustion engines are harmful to the environment. The chief pollutants are CO, NOx, unburnt hydrocarbons HC, and with diesel engines also the soot particles. So in emissions of greenhouse gases called as CO2 and are proportional to the fuel consumption. So this is the table that is shown by the Euro 4 norms, which is showing the exhaust gas threshold values for passenger cars. So this is the maximum limit in grams per kilometer of vehicle or fuel utilized for SI and CI engines. So a vehicle should not cross these limits in order to stand in the Euro 4 norms. And this is the performance map of an engine. So in this performance map, the information is found out by conducting a series of tests on the engine, and the program from these tests is called the engine mapping. These tests determine the performance and investigate the effects of each variable that has some bearing on the output of the engine. When the effects are known, the settings that give the best performance can be determined and recorded. A dynamometer is essential equipment for conducting these tests since it can be programmed to simulate the road conditions. The engine is loaded by means of a dynamometer, and the torque, power output, economy, and emissions are measured against speed and other factors that they have certain effect on the engine output. The performance curves are plotted manually or by computer represented graphically. The behavior of the engine, which is subjected to the changes in the following parameters. The parameters could be the speed, the load, ignition timing, air fuel ratio, engine and ambient temperature. So in this figure, if we can see the x-axis, which is showing the engine speed, the y-axis on the left shows the engine torque, and the y-axis on the left right shows the engine power required. So altogether, these are the three parameters what we are considering for today's engine map diagram. And in this, for time being, let us discuss about the torque or consumption loop, which we are getting here. So to plot this map, the air fuel ratio is varied and the fuel consumption and torque output are measured for each setting. Speed is kept constant during each test so that a series of tests is required to be conducted to cover the engine operating range. And this shows a fish hook shaped map which is plotted for the engine operating under full load. Before the exhaust emission regulation were introduced, the air fuel mixture used was based on the ratios required for either maximum power or maximum economy. Unfortunately, the 12 to 15% enrichment from the chemically correct ratio to provide maximum power also produces a high emission of COHC NOx in the exhaust gas. So these in this figure we have shown the three types of lines which are the different test scenarios conducted. So the actual consumption oriented, which is shown in the dark uh, thick black line, is the consumption oriented line, and the performance curve is shown in the middle one, the dashed line, and the expected curve is shown at the bottom. So actually what happens here is the consumption oriented, which is the already discussed as the fish hook, is the thick line which is shown in this shape, and the performance oriented, which is shown as the dashed dot line, which is at the bottom, in which we are having a maximum um, power. And then based on these two conditions, we are maintaining a performance oriented compromise in between those two. And next, the scan tool is nothing but the OBD management, which we'll be using in order to measure the emissions. So every assembly group in the powertrain is relevant to OBD as soon as it exhibits its own control unit. This brings the transmission into the OBD's focus as well. For example, faulty regulation of the torque converter lockup clutch of a conventional automatic transmission can have a negative influence on consumption and exhaust gas. To guarantee proper transmission functions, diagnostic routines are constantly running in the transmission control unit that monitor all actuators and sensors for functionality, plausibility, and electrical faults. And if necessary, activate replacement of emergency functions. Exhaust gas relevant information are also processed and relayed by the program module OBD management. For the onboard diagnostics, also causing the MIL to activate OBD calibration. Complies with requirements pertaining to both the vehicles and legislation. The way that the OBD information and the transmission is processed in the control unit network depends on the vehicle. This figure shows the example of a corporation of engine and transmission control units. Here, OBD management of transmission functions runs independently in the transmission, while transmission relevant OBD calibration is subdivided between the transmission control unit and the engine control unit. The MIL activation is controlled solely by the ECU. In the US, the forerunner with respect to exhaust gas legislation for motor vehicles is CARB, the California Air Resources Board. In the case of California's LEV legislations, which are the low emission vehicles, there are no consistent threshold values for all new vehicles, such as in the case of European directives. Rather, there are different threshold values, and their gradual implementation. Vehicle manufacturers are obligated to maintain an average fleet of emission standards of all vehicles sold. And next comes the ideal working of the subsystem. So before going to know about the ideal working of the subsystem, there are a few considerations that one should know about the gearbox theory, because the ultimate aim of the automatic transmission is purely dependent on the gearbox. So to know the about the gearbox, perfect theory of gearbox related things are very much mandatory. So some important notifications or the equations that are mandatory are the ratio which we come across the gearbox is the input speed by output speed, and the gear step, which is the ratio of lower gear to the ratio of higher gear. So let us go in detail. The gear step tells you a lot how the gearbox behaves. When you keep the engine RPM constant, gear step tells you how faster you are and go in upper gear compared to lower gear. On the other hand, it tells you how much engine RPM does in upshifting or increasing in downshifting. More detail, there is a speed difference in the gearbox parts, which you engage, disengage current gear and try to shift to a new gear. This shift difference must be reduced to zero before shift can be completed, and gear shift tells the how large the difference you are about to reduce. And there are two types of methods in which the gearbox has been designed, which are the geometrical gear steps and the progressive gear steps. So the geometrical gear steps means that every gear step has between the two sequential gears is also the same. So for example, if you consider a uh, 5 speed or 10 speed automatic transmission, so the gear step which is having from 1 to 2 is equal to the gear step of 2 to 3, and which is equal to a 3 to 4 and 4 to 5 and so on. If it is a 10 gear, so 1 to 2 will be equal to 2 to 3 will be equal to 9 to 10 and 8 to 9. So this is the sequence what a geometrical gear step follows. So trucks need actually large overall gear ratio, which will be ranging from 15 to 20, which means a great number of gears, 9 or more, to prevent too large gear steps. With one of the main gearbox, you can't get enough gears, so you need a splitter or a range change unit or both. Splitter unit are a small gear step, which means there are low and high version of each gears of the main gearbox. So in the splitter, the gears will be of order 1L, 1H, 2L, 2H, which represents the L represents the low and H represents the high. So you have alternately easy splitter shifts without the main shift lever movement, and compound shifts with splitter and main box. The range change unit, which is also called as a large gear step, which means that you have to go through the gears of main gearbox twice in upshifting procedure, first in low range and again in the high range. Next comes the progressive gear steps. The progressive gear steps means that the higher gear, the smaller gear step between the gears. This is done by basic gear step and progressive gear factor. So if we consider the example of a 5-speed transmission, in the gear step 4 to 5, there is only basic gear step. Gear step 3 to 4 is basic gear step into progressive factor. Gear step 2 to 3 is basic gear step into progressive factor square. And final gear step 1 to 2 is basic gear step into progression factor power cube. But also the gearbox is progressive gear steps has some problems. You can't use either splitter or range change unit with main gearbox, that the progressive gear steps are at least progression must be very small. For example, if we are considering a 10-speed automatic transmission gear, um, which is having a gear step of 4 to 5, will be as small as the gear step of 9 to 10, but in higher gear step, the 6 to 7 will be as large as the gear of 1 to 2. You can make main gearbox with progressive gear steps, but it works good in high range only, while gear step 6 to 7 can't be too high. In low range gear step 1 to 2, will be a little bit too small, but problem won't diminish during the upshifting because gear steps get smaller and smaller due to the progression. So every gear step are is in low range is too small. So the better conclusion for using of this will be, as long as number of gears is 7 or less, the best solution is the progressive gear steps. When you need 8 or more solutions in the main gearbox with splitter or range change unit, and geometrical gear step or small progression in gear steps, when you need 12 gears or more, solution is main gearbox, splitter, and range change unit with geometrical gear steps. And now let's go in detail with the automatic transmission and its components. So automatic transmission and transaxles have similar components. The three basic parts includes the torque converter, gear train, which is called as the planetary gear sets, and hydraulic system. The torque converter connects the crank and transmits the engine power to the gear train. The hydraulic pressure acting through the automatic transmission fluid in the transmission or transaxle produces the shifts. This diagram depicts the gear shift mode of a vehicle in which we are having a uh, gear shift rod, and we can see the P, R, N, D to L, which are having their own significance. The P represents the parking brake, R represents the reverse gear, N represents the neutral, D represents the drive mode, and S represents the uh, press the shift lever release button. So let's go in detail with the torque converter. Torque converter is a form of fluid coupling. It uses a fluid such as ATF and vane rotors to transmit power between shafts. The torque converter is filled with ATF. When the engine runs, power flows from the crankshaft through the fluid to the transmission input shaft. Torque converter can be divided into three main members, which are the impeller, turbine, and stator. So the impeller is also known as the pump, is the driving member and that rotates with the engine. The turbine, the impeller vanes pick up fluid in the converter housing and direct it towards the turbine. Unless the torque converter is locked, the turbine is normally turned slower than the impeller. Starter, fluid flows drives the turbine, and when the flow between the impeller and turbine is adequate, the turbine rotates and turns the transmission into the input shaft. A torque converter contains the starter and a reactor and a reaction chamber mounted on the one-way clutch. Then every torque converter requires a transmission oil, in which will be showing like this. So when the engine runs, the fluid between the vanes in the impeller is thrown outward by the centrifugal force. So the fluid strikes the turbine vanes. This action produces the rotating force on the turbine and the transmission input shaft attached to it. The vanes then direct the fluid towards the center of the turbine and back towards the center of the impeller. This is how the pump and the transmission oil takes part in driving the transmission system. And next comes the stator. To make the torque converter more efficient, a third member or stationary reactor called stator is placed between the impeller and turbine. The stator has curved vanes that changes the direction of the fluid after it leaves the turbine. This causes the fluid to pass through the impeller and then push to the turbine vanes against again with a helping force that aid the rotation. The result is torque multiplication under certain conditions. So what is meant by torque multiplication? So if we consider an example, suppose 1.35 newtons of torque entering the impeller, the turbine delivers more than 2.7 newton meter of torque to the transmission input shaft. Torque multiplication occurs only when the impeller turns faster than the turbine. If you look at the figure at the right, fluid pumped in the turbine by the impeller only creates the rotary fluid flow, but also vortex flow that increases the efficiency of the torque converter. Next comes the torque converter clutch. The main function of TCC is a lockup. Torque converter eliminates the 10% slip that takes place between the impeller and the turbine at the coupling stage. The engagement of a clutch between the impeller and the turbine assembly greatly improves the fuel economy and reduces operational heat and engine speed. The lockup torque converter has a lockup or clutch piston with a lining of a friction material. The piston or plate attaches to the turbine hub. Isolator springs helps dampen the shocks of the engagement as the torque converter locks. They also dampen out the power pulse from the engine while the torque converter is locked. The clutch is controlled by hydraulic valves which are controlled by the PCM. The PCM monitors the operating conditions and controls lockup according to those conditions. So when the torque converter is not locked, that is the clutch is disengaged, the fluid enters the converter and moves to the front side of the piston, keeping it away from the shell or cover. Fluid flow continues around the piston to the rear side and exists between the neck of the torque converter and the stator support. During the lockup mode or the clutch engaged mode, the shift valve moves and reverses the fluid path. This causes the fluid to move to the rear of the piston, pushing it forward to apply the clutch to the shell and allowing for lockup. Fluid from the front side of the piston exists through the turbine shaft that is now vented at the switch valve. This is the basic design principle of an automatic transmission, which is controlled by the control unit. So the control unit senses the uh, required amount of pressurized oil that is required for the lockup clutch and the torque converter and the brakes and clutches. So the pump, the control unit sends the information and the pump releases the adequate amount of transmission oil and sends it to the required path zones. And these are the very popular transmission system dimensions, which is showing the phase to mount distance and the overall length. So these are the basic models of transmission systems, automatic transmission systems of various companies, which are showing the phase mount, phase to mount distance and the overall length. And these are the some of the electronics and instrumentation parts which are involved in the automatic transmission. Those though they are certain ample number of mechanical parts though, but this is also controlled by the electronics as well. So the first comes the push belt, in which The push belt can be seen in mostly in the CVT. The push belt transmits the engine output to the drive axle. And next shown here is the variable force transmission solenoid, which is known as VTS, which controls the pilot pressure in automatic transmissions. And then the transmission control unit, which controls the overall transmission system. On many transmissions, a gear change is made by means of a hydraulic controller activated by a transmission control unit. And next, the pressure or flow activated direct electric shift control. The pressure or flow activated direct electric shift control serves as an actuator for pressure or throughput control on automatic transmissions. And the last comes the transmission sensors. The transmission speed sensors detect the input, output, or intermediate speed of the transmission and transmit this information to the transmission control unit TCU. This is the basic gear shift algorithm which is used in designing the modeling the automatic transmission of a 4-speed gearbox. And inside the automatic transmission model, which is modeled in a MATLAB, uh, a force a MATLAB function block is required in which a gear shift logic is to be written. So that gear shift logic, which is called as a gear shift algorithm, is to be coded in the MATLAB code in the manner what it is shown here. So in this, if we can see, as I'm saying that this is a 4-speed gearbox, here function of gear equal to FCN of, this is the code what we are supposed to write here, FCN of U1, U2, U3, U4. So if you want to model a 10-speed gearbox, then you have to give 10 inputs over here, U1, U2, U3, U4, U5, U6 till U10. So according to that, you have to represent the states as state 0, state 1, state 2, state -1. And then we are supposed to write a genetic code for this system. And some independent manufacturers of automotive transmissions um, or which are manufacturing both mechanical and automatic transmission systems are given here, in which we can find the ZF, General Motors, Aisin, Jatco, Allison, 810, Twin Disc, so on and so forth, in terms of passenger cars and the commercial vehicle segments. And these are the references what I have taken in this, and mostly I have considered most of the topic from the a textbook which is a Springer second edition called as Automotive Transmissions, written by Harald Naumer and Robert Bosch Systems. Thank you.